Hey 350, it's Chris here. Today we're going to go over Recitation 7, which is going to deal with real-time operating systems, tasks, scheduling algorithms, a little bit about concurrency, and then we'll talk about race conditions, semaphores, and mutexes. We're probably going to spend the bulk of this recitation dealing with scheduling, so if you are comfortable with scheduling and came here for concurrency, just skip ahead till you start seeing the words semaphores or mutexes in the notes pan on the left half of the screen. So right off the bat, we're going to talk about tasks. So real-time operating systems are considered real-time operating systems because compared to normal operating systems, they have these guarantees with them about how tasks are executed. And tasks are our way of talking about concurrent processes, concurrent resources, things like that. Normally, when we talk about operating systems, we don't talk about tasks. We're talking about processes, we're talking about threads. We have very specific or vague language. Tasks are kind of weird because they're neither telling you exactly how it's implemented, nor is it telling you absolutely nothing. Tasks just have the four main pieces about them. They have a deadline, they have an execution time, they have a period, which is how frequently we have to redo these deadlines and execution times, and they have a priority. So you can kind of think about a task in daily life as just something you have to get done. For example, you can think about 350 as a series of tasks. Every 2 weeks, give or take, you have a lab. That means you have a 2-week deadline. It might take you a certain amount of time to complete that lab. Maybe, I'm going to throw a ridiculous number out here, but maybe it takes you 72 hours nonstop work to complete every lab. Hopefully that's not the case. If it is the case, please contact us, but maybe it takes you 72 hours continuous work to complete the lab. You have a deadline of once every 2 weeks, and then you have a period, which is how frequently it occurs. Now, in this situation, as soon as you get your lab, your next lab comes out. That means your period is equivalent to your deadline. If, for example, we staggered the labs and gave you 2 weeks to do each lab, but we gave you the next lab in the middle of the other lab's execution time, then we would have a period of 1 week. So the example of that would be if we had, if we had this as your A4S lab, this as your theremin lab, and then this would be your Pong lab. Each of them, you're given 2 weeks notice in terms of you have 2 weeks to begin starting on it and get it done. So it has a 2-week deadline. But we're giving you each of these assignments, so their due dates are all 2 weeks down the line, but we're giving them to you at this sort of staggered thing. So that would be a period of 2. Now, for this class, we're actually not going to be dealing that much with situations where your period and your deadline don't agree. So unless we say otherwise, we're probably just going to give you either the period of the task in the execution of the task or the deadline of the task in the execution of the task. And you can assume if you're not given the period or the deadline and you're given the other one that they're equivalent. So in that case, and I'll grab my eraser here, it's no longer staggered like that. And instead you would have A4S and then theremin. And then you would have Pong. And that kind of makes sense if you think about it, because it's kind of weird to have a task that you have to get done while the other task is coming out. But why do we have tasks in the first place? Our aim with a real-time operating system is that if we can formulate the things that need to be accomplished, these maybe they're processes, maybe they're threads or whatever, if we can formulate the different parallel tasks that need to be done in this method, we can really quickly check, can these tasks be done given the amount of time we expect them to take, how often they're going to need to be done, what their deadlines are. Do we think it can be done? And RTOSs are our solution to this. So RTOSs have to deal with something with scheduling. They have different solutions to this, so you can have different algorithms for how an RTOS decides how to schedule tasks. Take, for example, this situation where we have our first task, task 1. It has a deadline. It takes the amount of time you need to execute the task is 1 tick, but you need 4 ticks before the deadline, and then after 4 ticks, it gets re-upped and you have to do it again. So we can view it this way, and there are a couple ways to do this. In the first tick, we have to decide we can only schedule 1 task. Do we schedule task 1, or do we schedule task 2, which has an execution time of 2 and a deadline of 8? Now, in RMS scheduling, which you should have covered in lecture, which is rate monotonic scheduling, we're going to talk about tasks in terms of their priority. And priority is this fixed notion. Normally, the tasks that are being done more frequently in rate monotonic scheduling are going to have the highest priority. There's a couple exceptions to that. Those are mostly if it's explicitly stated, and if it's a interrupt. So interrupts are a little bit weird. We'll get onto that. We'll touch on those in a later recitation. But for right now, you can kind of think about rate monotonic scheduling as, let's get the fast things done first and then move on to the slow things when we have time. So we can start to fill this out just saying, this gets done at a faster period. It's also hinted at you, it's task number 1. So it has the highest priority task. It's the task of priority 1. And then we have a task of priority 2. So we're going to do the task of priority 1 first. So we're going to schedule this, draw a little block here, and we get it done and out of the way. And now we move on to tick 2. So we go from tick 1 to tick 2. At tick 2, task 1 has already been scheduled, and so this is satisfied. And task 2 is the only one that's up in the air. So we're going to schedule task 2. So we check it off for 1, but it needs 2 blocks to do execution. So we move on to tick 3. Task 1 is nowhere to be seen. It would have had highest priority, but it's completely content. So we can move on to task 2 again. And at this point, task 2 is satisfied. And it's content all the way up until, so we can draw this. Task 1 is content till its deadline, which is 4 right here. And task 2 is good all the way up until its deadline, which is number 8. And so now we move on to tick 4. Nothing gets scheduled. That's completely fine. We can have an idle state. And then we move on to tick 5. Now at tick 5, our task number 1, which has a period of 4, has now re-upped. And so it now has a new period. It has a new deadline. Its new deadline is 4 from the 4th. So it's going to be due at the 4, at the 8, at the 12, at the 16, and so on and so forth. So we're going to schedule it here. And then it's satisfied, so we can keep doing this. And we get to 8. An interesting thing happens. And this is a weird oddity that happens with RMS. Doesn't necessarily happen with EDF. But it's that with RMF, we get this repetition. of scheduling. So once 8 happens, we have both of the tasks have their deadlines elapse at the same time, which means it's identical to our starting condition. And we can say in this sort of inductive reasoning, if it's identical to our starting condition, then tick 9 will be identical to our tick 1, and tick 10 will be identical to our tick 2, because we're starting both of them off on the same mark. They've both satisfied all their deadlines, and now they have new deadlines. So this becomes kind of a cycle, except now this is 9, this is, and so on and so forth. But it becomes a cyclical thing, and this happens because might be messing up, least common multiple, which is 4 can go into 8 2 times, so between 4 and 8, the least common multiple is 8. Let me just... Yeah. Want to make sure I'm using my right 5th grade math skills. But yeah, it's the LCM. So the LCM of all of the periods of all of the tasks that are being considered is going to tell you when will the rate monotonic scheduling repeat. And so if you can schedule every single thing before everything can be scheduled, everything can be done properly by rate monotonic scheduling before the least common multiple, then you know inductively, since everything else after then will just be repeating this chunk over and over again as a cycle, then you can just say, well, it's good to the least common multiple, therefore it's good indefinitely. So this is a sufficient proof to say that these two tasks are good under RMS and EDF. That being said, it's not a great proof. I could really easily change this from 4 to 5, and now you have to redo it, and the least common multiple of 4 and 5, I've just increased it to the point where it's like, well, now you have to go all the way up to 40, because the least common multiple of 5 and 8 is 40, and so now you're kind of in a bind where you now have to draw out this massive scheduling table. Now it's much more complicated. And so we want to ask ourselves, what's a better way of doing what we just did right here mathematically so that we can better assure ourselves that we haven't broken schedulability. So for right now, I'm just going to revert this back to 4. We'll come back to the 5 example later. But so we have task 4.1. Task 1 has a period and execution time of 4. Sorry, a period and a deadline of 4, and an execution time of 1. Task 2 has a period and a deadline of 8, and execution time of 2. We want to ask ourselves, how can we prove this mathematically without going through all the work and drawing it out to the least common multiple? Well, we have 2 solutions here. Once we get onto EDF, it will be easier, but for rate monotonic, it's a little annoying. We actually have to prove it kind of once or twice over. So we have 2 tests. We have the upper bound test, and this is fast, but can yield inconclusive. We have this upper bound test, really great, or sorry, utilization bound. But then we also have another test, which is much more complicated, which we'll call the response time test, or RTT. And this is slow, annoying, always right. So we have these 2 tests we can use. First, I'm going to start with the utilization bound test because it's not as intuitive, but it is very useful. So the utilization bound test says the following. We can talk about the utilization of a task as, you know, utilization of T1 is how often, assuming everything's scheduled properly, how often is this task actually being executed? So for task 1, it exists in this sort of repetition of it does something for 1 tick and it takes 4 ticks, and then the next cycle it does something for 1 tick, takes 4 ticks to schedule it in, keeps on doing this. And so we can talk about it that if it's doing something for 1 of the 4 ticks, it has a utilization of about 1 in 4 or 25% of the time it's being utilized. So task 1 is utilizing the resources, and most of the time it's the CPU, 25% of the time. We can also talk about task 2, in the same vein, has, it takes 2 ticks to do whatever it's doing, and it has 8 ticks to do it in, which simplifies also down to 25% of the time. Task 2 is utilizing the resources. So we have this 25-25. So in total, between task 1 and task 2, the total utilization for this task set is going to be a big U, and I'm just going to it's going to be the sum of utilization of I in the task set. So that's just going to be 25 plus 25, which is the individual utilizations, means the following. Big utilization is 50% for 2 tasks. So some people who are much smarter than me at some point realized you don't always need to know everything about tasks to be able to know whether or not you can schedule it. For example, and you can kind of think this through, if I have this task set that's saying, it has something to get done. Let's say we have this task, and I'm going to come up with an example. I'm going to call this TE for error. And I'm going to say that T error is going to say that, once every 5 ticks, or actually I'll simplify it, it's going to be once every 2 ticks, it's going to get done 3 things. Well, what's the utilization of that? That is 3 over 2. That's 150% utilization. You can kind of think about that for a bit and say, how is it doing something 150% of the time? It doesn't make sense. So you, me, we all kind of intuitively can say that for one task, for a single task, it's weird for it to be over 100% utilization. And we can go one step further. For 2 tasks, it's weird that they would sum up and be 100% utilization. 100%, over 100% utilization doesn't make sense, and it shouldn't be possible. So we have this idea that, right off the bat, if anything's over 100% utilization, it can't get scheduled. Well, some really smart people sat down and said, we can go one step further. Theoretically, if we knew for every number of tasks that need to get done, there should be some point where we can say, as long as the utilization's below this number, we're all good. And that's where the UB test comes from. So we have this fancy formula here that I'm just going to call, it's n to the 2 over n minus 1. I'm going to call this UB of n. And we can treat UB of n as this number which says if the utilization for n tasks is less than or equal to this number, then we know inherently it must be schedulable. And the beauty of this is the upper bound test, the utilization bound test, tells us the following. If we have these series of tasks, and we plot this spectrum where the spectrum shows the utilization, the total utilization of a task set. We have this spectrum where if the total utilization is above 100%, then we know it's not schedulable. And if the utilization is below this UB bound for the number of, which is only dependent on the number of tasks that we have, that we're scheduling, then we're in the good zone, and it is schedulable. Let me give you an example. So let's say I have one task. Not multiple, just one task. If I had one task, and it just needs to get scheduled 99% of the time, inherently, does it matter? It doesn't really matter if that one task, let's say T3, utilization 3, 99%. It doesn't really matter, since it's only one task, we don't really care about like, oh, how frequently is it getting scheduled? What's the period? What's the execution time? You know, how much time do you have for the deadline? Do the period and the deadline agree? We don't really care about any of this. We can just say definitively, oh, it's one thing. There's nothing else in contention. It's trying to get this done, and it has 1% free time. Yeah, it can be scheduled. So we can definitively just say, well, 99% is less than 100%. That makes sense to us. So my question for you is, we can verify this by saying, what's the UB of 1? Well, the UB of 1 is 1 to the 1 minus 1, which is equivalent to 1, or 100%. Which, as we've previously stated, as long as U3 is less than or equal to upper bound of 1, we know definitively it is schedulable. Now, this gets more complicated when we deal with our previous task set. So our previous task set had said 50% utilization. So let's try and prove that to us. If we just knew that it was 50% utilization, could we say definitively that it could be scheduled? Well, UB of 2 is going to be 2 times 2 to the 1/2 minus 1. Let's just whip out our calculators. I'm just going to do 2 times 2 to the 0.5 minus 1. It's going to be something like approximately, I'm just going to say 82.8%. And 82.8%, 50% is less than or equal to 82.8%, which means U is less than UB of 2, which means we don't even have to consider anything about the period, the execution time, deadline, and we don't care any of that. We don't even care about the priorities. We're just saying intuitively, if you have a 50%, if you have this task that is this task set and it's only using resources 50% of the time, it must be schedulable. And so we're just going to say U is schedulable. Now, I've talked a lot about schedulability and schedulable and unschedulable tasks. And then we have this weird region here. Now this weird region is kind of the point where you don't know if it's not schedulable, but you also don't know if it's schedulable. And that's where the UB test yields an inconclusive result. So when you're thinking about how to determine schedulability for a task set, you want to say, I'm going to take in all my tasks, I'm going to try the UB test first if this is an RMS algorithm. And if the UB test doesn't work, if it's inconclusive, then I have to do the RTT test, which we can still do the RTT test on normal task sets. We just normally don't. So what does the RTT test do? It's commonly referred to as the response time test, and its goal is to determine for every task in the task set what is the maximum amount of time it would take for this task to be done. And so we're just going to check to see with the response time task, for task 1, how much will it ever have to wait? Well, it's task 1. It has the highest priority. It never has to wait. So the only thing that factors into task 1 is going to be its own execution time. Task 2 might have to wait on task 1. But once task 1 gets done, it can probably complete. And as you can kind of see, the response time test has this kind of thought process where you say, I want to assert that each of my tasks can get done in their allotted amount of time. They can all finish before their deadlines at the longest stretch they have to deal with. And the definition of the longest stretch is when all of the higher priority tasks also are trying to get done too. So, I'll come up with something slightly different for the RTT test. We're going to go, task 1 is going to be 1,3. Task 2 is going to be 1,2. Let's just check 1,3, 1,2. Okay, so as you can see, this task set, the utilization bound for this task set is going to be 1/3 plus 1/2, which is equal to 83.3%. If we scroll up, UB of 2 is going to be 82.8%, which means U is greater than, it's greater than our UB, but it's less than our 100% upper bound, saying that if something has more than 100% utilization, it's impossible to schedule. So this is perfectly inconclusive by our UB test. Now, I see where your brain might be going. Chris, do we have to do the response time test? Can't we just draw this out? And let's take a second and actually draw it out just to see what we would expect our response time test to say. So if we draw this out, we have task 1, task 2, and as we can see, 3 and 2 are nice because the least common multiple of them is 6. So we actually only have to plan for 6 ticks. So 1, 2, 3, that's a deadline for, let's see, these should be swapped because this one's more frequently, occurs more frequently. So I'm just going to go 1, 2, 3, going to mark that one, 4, going to mark that one, 5, 6, going to mark it on each. So that's how long it takes for these deadlines to overlap. That's how long it would take for this to cycle. So right off the bat, they each only need one block to occur. So I'm just going to do 1. Then 2 gets scheduled. gets scheduled, this gets scheduled. Perfect. Okay, and each of these can schedule. We'd expect this to be schedulable. And this, they each break, they finish everything in time. So but how do we format this mathematically speaking? So we have this idea, which is A0 is only going to care about, in the response time test, we have this notion of A1, A2, A3, A4. And all of these care about some task in some task set. So we're going to refer to a couple things here. We're going to refer to I, which is the task in question. We're also going to refer to another thing, which is going to be N, and N is going to be iterations of RTT. And I'm saying iterations because the response time test requires you to basically keep computing. The way the response time test works is you say, well, how long would it take for my task to complete? This is like big picture. It says, how long would it take for my task to complete? Assuming everything of higher priority executes fully, and then I execute. And then with that, you come up with an answer to that question. And that is A0, which is how long would it take for my task to complete given everything above it in priority executes before it. And then A1 is you say, okay, given that I take that much time, are there any tasks of higher priority that would actually execute twice or 3 times or 4 times? Would that change the amount of executions of the higher priority tasks? And there might be a task that does execute more frequently, that might come into play. And then you say, okay, now with that adjusted time, so you basically get this trade-off where you say, oh, it would take this amount of time to execute, but if it actually took that amount of time to execute, it would take even longer to execute because the higher priority tasks would maybe go once more, twice more, 3 times more. And so you just keep on going and iterating. A is your guess. So A sub n is where you, let's say A sub n is your iteration. And then A sub n plus 1 is your guess as to, well, given what I figured out would be the time in A sub n, how much would it actually take? And then you keep on doing this and going through this and keep on coming up with more and more guesses until A sub n is equal to A sub n plus 1. That happens when your guess when the change you made to your guess no longer affects the overall response time. And that is when you basically say, my response time has stabilized. This is a solid guess. This is a stable idea that if it were to take this amount of time, then we know the following, which is if it would take this amount of time to do the task, these are all the tasks that would get done in the way, this is how long it would take, and this is an actual good idea of how long it would take at the largest amount for my task to culminate. And if A sub n, which is the amount of time it takes for your task to execute, if that is less than E, where E is the, not E, if it's less than D, where D is the deadline of your task, then you're good. So as long as it's less than or equal to your deadline, you're good. So this is the idea. So we're just going to go ahead and do it for this sample. It's a little straightforward because this is a sample with 2, but when it comes out to the samples with 3, that's where you're going to want to look at this formula in depth. So we're going to start, it's task 1 is, okay, so we're going to start task 1. Schedulable. And we're just going to say A0 is equal to sum from j equals 1 to 1, where 1 is our task's priority. Because as we said, I is the task in question. Well, that's just summing up C, which is the execution time of task 1. So this sum is actually just C1. You can kind of look at it straightforward. And C1 is the execution time of task 1, which is given as 1. So A0 equals 1. But we still have to iterate. A1 is equal to C1 plus the sum from 1 minus 1, which is 0, of j equal to 1 from this, which is the ceiling. Never forget the ceiling. People do it all the time. They end up with fractions, and we don't care about the fractions. We only want the ceiling. The ceil function, a to the n, and it is going to be 0 of Cj. Now, if you look at this sum, you can tell right ahead, it's summing from 1 to 0. That means that this entire sum doesn't exist, which means A1 equals C1 equals 1, A0 equals A1 equals 1, terminates. So we know that the largest execution time of task 1 is just going to be 1. And now that we know that this is true, we can do the quick check, which is our response time of task 1 is going to be 1, which is less than deadline of task 1, because deadline of task 1 is given as 2, and 2 is less than 1. You all probably knew this ahead of time, which was, if you just think about it, it's the highest priority task. How long would it ever take it to execute? Well, it's not waiting on anyone, so it only takes its execution time, which is 1. 1's less than 2. We're all good. Now, that's not where this response time test ends, because all we've proven up until now is that task 1 will get done on time. We have to prove that task 1 will get done on time, and task 2 will always get done on time. So now, is task 2 schedulable? Okay, so now we have to do A0 is equal to sum from 2, j equals 1, Cj. This is going to be C1 plus C2. What's C1? What's C2? Well, A0, we're given both of the execution times of task 1 is 1, and task 2 is 2, therefore A0 is 2. A1 is now going to be equal to Ci, which is the execution time of I, which we're looking at I equals 2. So it's going to be C2 plus the sum from 1, starting at j equals 1, of ceil of A to the 0 divided by T, J, C, J. This is pretty straightforward. The sum reduces, we actually just have A0 divided by t, which is the amount of time it takes to execute the task. You can kind of think about t is the period, which is given as 2 times the cost of completing the task, the execution time of the task, which is 1, and C2 is given as 1. So A1 is equal to this. Now A0 is given as, we already computed it, it's 2, so we have 2 divided by 2 plus 1 equals A1. That is equal to 2 divided by 2 is 1, 1 rounded up, because that's what the ceiling function does, is also 1. 1 plus 1 is 2. So A1 equals 2, and A naught equals 2. Therefore, A1 equals A naught. Test terminates. Okay. And now we also have to check the following, which is the response time tests of task 2 is equal to 2, which is less than the deadline of task 2, because the deadline of task 2 equals 3. 3 is less than 2. Therefore, task 2 is schedulable. Okay, so now we've asserted all of these things. We've said task 1 is schedulable, we've said task 2 is schedulable. Since no other task is in the system and all of the tasks are schedulable by the response time test, all's good. So we're just going to say task 1 and 2 are schedulable. Therefore, the entire task set is schedulable. And I should be clarifying this periodically, but it's under RMS. Before we go on to EDF, I just want to give a little bit of a mention of a couple cheats here and there with RMS. So up until now, I've shown you can prove RMS schedulability 3 ways. Pictorially, which gets annoying after when you have, problematic least common multiples. So pictorially works well, but once you start to get to more than like 12, you don't want to do things pictorially. The UB test is useful, but it can yield inconclusive, and actually most of the time it's going to yield inconclusive. And the response time test is that thing that always works, but it's, as you've seen, we have to do it for every single task, and it gets really annoying, but it does give us a definitive answer. Rate monotonic scheduling is a little bit annoying. So what are some other options out there? We have EDF, which is also the same as least laxity first, which is a thing we won't cover in this class, but if it ever does come up, it's roughly equivalent to EDF. And what EDF says is EDF is earliest deadline first, and all it says is instead of having this fixed notion of this has a priority and this has a different priority and these things have, this task always goes over this task. Instead, EDF praises this thing which is called dynamic priorities. If you think about it, our previous RMS example had what are called static priorities. A task is given a priority at the beginning, and we schedule things based on that priority. EDF says, I'm going to compute in live time which things should be done first. And it's kind of intuitive in the way that it does that. I like to call EDF the homework algorithm because it's how a lot of students figure out what homework to work on. Because it just says, what is due next? Because I'll just do that, get that out of the way, and then I'll work into the future. So I'll do what's done immediately, and then I'll do the thing due after that, and then I'll do the thing due after that. And so that's how EDF works. It's relatively straightforward. I'll do an example of EDF with let's try. So EDF actually wouldn't change this if you think about it, because right here, task 1 has the earliest deadline. Right here, task 2 has the earliest deadline. Here, task 2 has been satisfied and it's good, so task 1's going to go, because it has the earliest deadline. By the time it gets here, task 2 can be scheduled, task 1's been satisfied, and then task 1 is the only thing left to be scheduled. So EDF wouldn't really have an effect here. Sorry. It would have an effect, though, if we add a third task, and I'm just going to go ahead and add a third task. I'm going to call it 1.5, 1.2. Actually, I've shooken up, I think, the way the numbers cancel. How did I refer to the numbers? Yep. So 1.5, 1.2, and then 1.3. And I'm going to call this A, B, and C. The reason I'm doing this is because I just want to drill in your heads. There's no priority. There's no highest priority task. There's no second highest priority task. At every instance in time, we're going to recompute what has a higher priority. And so if we do this out, we have A, B, C, and I'm only going to do this up till 6. So I'll show you how to prove whether it's schedulable or not, but we're only going to do this up until 6. Just to show you what it would look like. So if you remember, we had some schedule like this, except now we're slipping in this new event because this is 5. So B has the earliest deadline. B is satisfied. Now we're only looking at C, which is over here, and A, which is over here. C has the earlier deadline. We're going to schedule it. It's now satisfied. The only thing left to do, we now have B comes back into the frame. Now all we care about is B and A. Between B and A, B has an earlier deadline. B is going to get scheduled. Now that B is satisfied, we have C. We're at this time tick right here. We have C and we have A. And now A has an earlier deadline than C. A is being executed less frequently than C. In rate monotonic scheduling, we would put C first and schedule it here, but in this, we're actually going to put A first because it has an earlier deadline. Then we're going to have B and C in contention. They both have the same deadline. There are different ways to settle this contention. Really, we don't care if the two tasks are the same. They have the same deadline. I would recommend just choose the task that has the higher frequency, but it won't have an effect. It's actually identical. The resulting task set should be fine. So we're just going to do C and then B. We could do it either way. It doesn't matter. Point being, we're always choosing whatever has the earliest deadline, and that's kind of the crux of the algorithm. So this is pretty straightforward, but how do we know if it's schedulable? This is why we love EDF. Because EDF has this really, really nice promise, which is straightforward, which is, well, what's the utilization of this? So utilization of A is a fifth, or 20%. Utilization of B is a half, or 50%. Utilization of C is a third, or 33.3 repeating percent. So what is the total utilization of this? It actually ends up being like 103.3 repeating percent. We know from our previous statement about RMS that this is not schedulable. So what if we change this? What if we reduced this down to maybe... What if we changed these deadlines around and we made this so it was an even 30%? What if we said this is going to be 3 and this is going to be 10? So now it's 3, 10. That's now perfect 30%. So if we did that, then the utilization would be 100%. In RMS, we can't make a guarantee on a utilization of 3 separate tasks, only under the assumption that's 100%. In EDF, as long as the utilization bound is below 100%, it's schedulable. So this actually works for EDF perfectly fine. Which means most of the time, actually, 100% of the time, if something is schedulable by RMS, it is schedulable by EDF. But it's not the same way around. Just because something's scheduled by EDF, all that means is that the utilization bound is below 100%. That doesn't tell us anything about, is it RMS schedulable? What's up? So why would we go with one versus the other? Well, if I like to think we want our task set to be schedulable, so why would we care about it being scheduled? I'd want our task set to be schedulable, so why would we want to put RMS over EDF? And the answer is actually rather intuitive. When we make our task set, not all of our tasks are equally important. And there are some tasks that need to be done really frequently that we don't care about. And so we might want to tweak RMS to handle that. There are also some tasks that are done infrequently that we just don't care about. The classic example of this is, let's say, we've had the coronavirus epidemic, and this is kind of a tweak on the classic example, but we have now at Penn this pass-fail system. Let's say you were to take one class pass-fail. Maybe it was a reading-heavy class that had relatively straightforward, easy assignments, but you had to read a lot of stuff, and you don't really care if you do well. Maybe you did well earlier on in the semester and you can coast in that class right now. But let's say you have this reading class. Theoretically, you don't have to do anything, but you're taking a pass-fail. And let's say they're giving you really, like, a lot of reading. They're giving you, 5 hours of reading every week, and you don't technically need to do this. And let's say you decided to take 350 for a grade. Just a reminder, we have no clue if you're doing it for a grade or not. So you're taking 350 for a grade, and let's say we give you a worksheet. And let's say the worksheet takes you, X amount of hours. And let's say we have a worksheet probably once every, 2 weeks, 2 weeks. interval, and let's say this is once a week. If you scheduled by RMS, you could say, well, I'm doing something for a grade, and the other one's pass-fail, and I think I can coast in this class. So you would probably say, I'm going to put this as the number 1 priority, and this is the number 2 priority. That being said, RMS would do this perfectly, and maybe you have other tasks that are happening, you have a lot of other things. RMS would say, I'm going to prioritize 350 over reading for the other class. And if, due to all of these other tasks that might be higher priority than these two tasks in general, if I have to choose between one of them, I'll bump reading. EDF won't do that. So EDF might do this thing where maybe you just don't, maybe a week comes, you don't have enough time to do all your homework. EDF snowballs, which is if you go over that 100% threshold, RMS would just ignore the task that was the lowest priority. If the lowest priority task can't be completed entirely, RMS doesn't care about it. It won't care that that's been messed up. But EDF actually will snowball, which means it will recognize, now let's say you turned in the reading late. Well, reading now has a negative deadline. Reading's deadline is now in the past. It has the highest priority, which means, oh no, I need to get done that reading. You do that entire 5-hour reading, you now have pushed out a lot of other tasks, and you basically now have to do everything late. So EDF doesn't do well for systems where the utilization bound could be over 100, because it will do this snowballing thing where now reading will get turned in late, but that means you don't have time to do 350, and 350 will be turned in late, which doesn't mean, all these things get turned in late, all just because you're doing it in this EDF fashion. You came upon a point in time where maybe one task took, maybe there was some interrupt or some weird task that happened, and now you're over 100% utilization. So that's kind of, EDF has this cons, which is snowball. And the pro for RMS is easy recovery. Now the cons for RMS, as we've stated, is this schedulability question, which is if you're going to do something by RMS, it's kind of on you, the programmer, to figure out, is this thing schedulable? The pros for EDF are actually straightforward. Easy scheduling. It's actually called optimality, which is that EDF is technically, if it is schedulable, EDF is the optimal. Meaning, if it is schedulable, it can be scheduled by EDF. Why don't we like it, aside from the snowballing mechanism? Because dynamically recomputing the scheduling for EDF is actually really difficult. You have to loop through all of your tasks and assess schedulability. So EDF, something is approximately O(n) time. You could do it quicker, but effectively EDF is this linear time algorithm where you have to go through each and everything, figure out its next deadline, and recompute it. RMS is actually straightforward because you could have basically a set of everything that is, you could have sort of like how would I put it, an ordered queue of things that are about to be schedulable, And by that I mean a set of things that you have satisfied their constraints and ordered by their newest time when they will have a good deadline, and then you could have a set of things um, ordered by their priority, and you would basically just check what's the highest priority item, and you're good. And you can actually do that relatively quickly. Um, it ends up being like a log n algorithm, so there are ways to fix EDF, but for the most part, there is this kind of relationship where EDF is a linear algorithm, RMS is a log n algorithm. Um, RMS requires less checking on everything and less recomputing, and so EDF tends to be the winner. Only in situations where you want to avoid having to check schedulability. RMS is the winner whenever you want a predictable system. You need good response time. You need it to be somewhat comparable to an operating system. Normal operating systems are much quicker because they don't use these deterministic scheduling algorithms with guarantees. What do I mean by that? So a normal OS, when we talk about concurrency, we don't talk about it in terms of tasks. We talk about it in terms of programs. And you don't have this sense. What a task gives you is it gives you, those four things. It was execution time, periodicity, deadlines, and sometimes priority. And you had these three things. The priority is flexible because you can have a dynamic scheduling algorithm like EDF, but the main things you get are the execution, the period, and the deadline. And operating systems don't really have a notion of that. Instead, when you start writing code for not real-time operating systems, you'll just have an idea of, oh, this thing has a certain priority, and that's it. You can just say it's a high priority task, it's a high priority process, it's a low priority process. That's all you really get out of it. And so you don't get these nice guarantees that you would have with an RTOS. That's why RTOSs are normally used in safety critical environments, working with basically if you're doing a job for something where safety is necessary and you can't accept failure, a real-time operating system is useful. That being said, I think a lot of times when people think RTOSs, they think about these kind of bare bone 350 RTOSs. There are more fleshed out operating systems. There's certainly a number of operating systems you could use that would have a couple more features. You're not going to want to, if you're writing code on something and you're doing RTOS work, you're not going to want to be running any like intense GUIs in it. And RTOS is the kind of thing where you boot it up and maybe you run it in parallel with the normal computer, with the normal operating system, and you do your RTOS work on one parallel side, and the rest of your work on the other. There are a couple Windows hypervisor operating RTOSs that work like this, where they're actually running on a separate core, and that's how they balance having an RTOS. And then anytime you want to do any complicated GUI stuff, you use pipes in between and use memory to communicate them back and forth. So this is just talking about the recovery problem. Now that we're talking about RTOSs in general, and I'm just going to really quickly go through this. Now that we're going on from this, we're going to talk about concurrency as a problem. So concurrency can be best summed up by you have a program that is doing multiple things at the same time. Maybe we can refer to it as having multiple tasks. It could be multiple programs executing simultaneously. It could also be a thread and another thread, and they're just executing simultaneously. Threads and programs are that kind of separation between threads and programs are the kind of things you would learn about in Sys 380. And if you're talking about threads specifically, also tasks, which are kind of an RTOS notion of threads, you're going to want to know about semaphores and mutexes. So a mutex is a way for you to basically say the following. Mutex is a way, and semaphores to an extent, to talk about a resource that might be needed by a task or two tasks from two different threads or anything like that. A mutex is this lock that one of the threads can grab and acquire, and it guarantees you that if one thread has it, the other thread doesn't. The beauty of this is you can lock a resource, execute some code, and unlock the resource, and you'll be guaranteed that no other thread had that resource while you were executing that code. One of the utilities of this is if you have a race condition between two different threads, or you just want to have two different, maybe you want a function that two threads have access to. You want only one thread to be able to execute that function at a given point in time. You would just lock a globally or static available mutex between those at the beginning of that function execution and release at the end of the function execution. The important thing I'm saying is you would lock a globally or a statically available mutex. And the reason I'm saying that is because the way threads work in memory is each thread has their own stack. They share a heap, and then you have code, which they share, and you have your statics / globals data. Normally those two are swapped, but what I'm getting at is if you create a mutex in sort of local function memory, you'd have one resource here and one resource here. That's not what we want. We want to refer to the same resource. So for mutexes, we want to refer to the same resource, so we'd want to store it either in the heap or the statics. So one example of this is actually the banker's algorithm. So this is an example of a kind of issue you could have with a race condition. And I'm going to show you kind of what we can do to address it. So in this situation, we have a relatively simple thing. So we have, we've decided we're smart programmers. We know how to write code, and I could deal with all ATMs sending requests to a central database, or each ATM could make their own change. So you can kind of think about this as one ATM requests to deposit $200. So this is the problem. One ATM requests to deposit $200. Another ATM requests to withdraw $100, and these are both happening on the same account. So they're both happening on the same account. We have one ATM that is putting money on it and another that is withdrawing from it. And they're both editing the same account. If we were to serialize this and have the deposit go through and then the withdrawal go through, we would expect the following, which is $100 left in the account. Because as we see here, the account has 0 to begin with. But what are some issues? Well, threads don't always execute in the same way. We could have them execute in an interleaved fashion. We could have them execute in various ways. So one thing we want to remember is we have balance, add money to balance. Really what that breaks down into is we have some, I just want to draw this here. We have deposit, and all a deposit's doing is it's incrementing the balance by the amount of money you give it, which is 200, and withdraw, which is decrementing it. But incrementation and decrementation actually get broken up into a lot of different lines of assembly code. It gets broken up into this, which is load from, wherever we stored balance into a local register, increment register, store register at balance. These are 3 separate actions. And the issue is this action here, the reading the balance, is not done in the same step as the incrementing the balance step. So what could happen is you could have both withdraw and deposit read the same balance. We could have it go, and I'll do it right here. We could have reg dep could read 0. We could have the withdraw register also read 0. The deposit register could, increment by 200, store reg deposit. And then we still have the rest of the withdraw to go through. So then we would say reg dep is going to be, we're going to subtract 100. So now at reg dep there's negative 100. And now we're going to store, reg with, store reg with. So right here, to balance. So at this point in time, balance equals 200. And at this point in time, balance equals minus 100. So we've deposited an amount of money that you would expect to result in, $100 in your bank account, and now you end up with, negative $100 in your bank account. And that's sort of the ATM problem. And the way we should fix this is we should make sure that they have, if you think about it, there's this resource. There's this notion of account. It's the same account. You shouldn't be able to change the account while someone else is changing the account. We want to stop this because these are 2 different critical sections that shouldn't be overlapping. These are critical parts of code that should not be allowed to run simultaneously. And the way we do this is we just say, we're going to have this mutex. We're going to call it account, and we're going to do account.lock, account.release, account.lock, and then account.release. And that addresses the ATM problem, because now when you try to deposit, we can't have reg dep with reg with, because the first thing that has to happen is acquire mutex for deposit. And now what happens is reg withdraw can't happen because it's stuck. It's waiting because it needs to acquire the mutex. And now release mutex, acquire mutex for withdrawal. And you can kind of see this play out because a mutex is something you need. You need to lock a mutex in order to proceed. It's an atomic action. You can't get through a mutex. Once it's locked, it's locked. Once it's released, it's released. And that actually helps fix a lot of our issues with the code. Semaphores are similar to mutexes. The only distinction with them, do it like that. The only distinction with semaphores, though, is instead of talking about this notion of locking and releasing a single resource, a semaphore is actually a collection of resources. You can think about it as a variable amount of mutexes. And when you refer to a semaphore, you say, I would like one of your, amount of semaphore resources. And when you release a mutex, when you decrement a semaphore, you're saying, actually, I would like to give one semaphore resource to the void. So you have this counter for a semaphore. And the way the counter for the semaphore works is a semaphore has an internal counter, and as it increments, you can if the counter is above, if the counter is a positive number, the semaphore can be acquired. If the semaphore is a non-positive number, if it's 0, if it's a negative number, it can't be acquired. And it can't be acquired until someone who has acquired a previous resource releases it and gives it back to the semaphore. The beauty of this is a semaphore can be used if you have something like a set of resources. For example, if you're in a barbershop and you're waiting to get a chair. There's a series of barbers with chairs, and maybe you're in line. You can queue yourself in the line by waiting on the semaphore, but the semaphore is not a single resource. It's all of the chairs that represent the barbershop. And when one person leaves a chair and goes to pay, they can release this set of resources, which are all the barbershop chairs. And so now one of those is available, and the next person who's been waiting on the semaphore will go and grab that chair. And so it's very useful if we're talking about a series of identical resources of a certain amount. One thing you can do with a lot of semaphores is you can say, I only want there to be one semaphore. You can set maxes to semaphores. And one of the utilities of this is you could have a semaphore that can have at most one item, which means it can be acquired, but as soon as it's acquired, it now has to be released. And that has an almost identical, it's called a binary semaphore. It's almost identical to a mutex. The only issue with a mutex is a mutex can be locked and unlocked, but it has to be unlocked by the process that's using it. And if it gets locked by a process, you have certain kinds of mutexes. Each programming language has a different kind of mutex sometimes, and there are things called reentrant mutexes, which are if I lock a mutex, can I lock it again, and will that basically freeze my program, or will it recognize that I already have that mutex? If you double lock a mutex, and you're able to continue working, that's called a reentrant mutex because it knows who its owner is and it recognizes that you've already locked it. In semaphores, there's no sort of concept about ownership. It's very much just a counter. Anyone can raise the counter, anyone can decrement the counter. It just means if you decrement it, you have to acquire whatever the counter was. Um, but I could have one process only decrement and one process only raise. You can't unlock another. It's complicated to unlock another person's mutex. That's kind of a programming language by programming language thing as to whether or not they allow that. But everyone can unlock. Everyone can increment another process's semaphore. And just going over, there are some terms for semaphores commonly referred to as P and V. P being the um, increment option, and V being the decrement option. If I remember correctly, semaphore P and V. So these are actually terms from the Dutch. Sorry, I might be mixing them up. Just want to make sure I'm not. Yes, okay, so P decrements it, V increments it. So V allows is the freeing of the resource, and P is the acquiring of the resource. Commonly, incrementation and decrementation are used. P and V are just historical terms that have stayed, and they come from the Dutch words. Aside from that, I think that's everything for recitation today. As a reminder, the lab is due on Friday. Please, please, please allot enough time to complete it. It's an annoying lab to get through if you haven't taken 240, and it will take a decent chunk of time just to get through how architecture should be emulated. If you're comfortable with emulating architecture, it probably won't take as much time, but in general, don't save it for like the last day or just Thursday. Please don't save it for Thursday. Thank you.